Welcome to the exciting lecture on computer architecture, the past, the present, and the future. I'm Professor Sarangi from IIT Delhi. So, what is computer architecture? Well, the study of computer architecture encompasses the study of computer processors and computer systems. So, what is a computer processor or a computer system? Well, it is pretty much everything. It is a mobile phone. A mobile phone is undoubtedly a computer processor and a computer system, a desktop or a laptop, and of course, the large servers that are a part of Amazon and Netflix, even they qualify as computer systems, and all of these things are taught in computer architecture. Some new additions have come to this list, like a smartwatch or a smart sensor. So, even they also fall broadly within the broad ambit or the broad realm of computer architecture. What do these computer systems do? Well, in the modern world, they do everything, starting from financial calculations to games to weather forecasting to just connecting to friends on the other side of the world, right? So nowadays we can get on Facebook and we can see what our friends in on the other side of the world in Europe or in the US are doing. That's great. In fact, one of the most common uses, one of the most common mobile apps in India has to do with astrology. So previously people had to go to astrologers, they had to figure out their date and time of birth, and based on that they used to predict how successful they would be in their job or careers or marriage. But now all of these things a computer can do very easily. So the computer can very easily make what is called a kundali for you, and then it can figure out what's going to happen. Are you going to pass this course or not? I mean, if you believe in astrology, that is. Computers are very useful for these things. How do computers do it? The crux of a computer is called the processor or the CPU, which can be thought of as the brain of the computer. So this has several peripherals attached to it that actually do most of the interfacing. We have the network, the keyboard, the mouse, the USB devices, the monitor, of course, the screen, the printer. This should have been the hard disk. I wrote network by mistake, but mentally erase it and think of it as the hard disk. So hard disk is where we store all our files and videos and all our homeworks. So everything is stored on the hard disk, and the hard disk is a very, very important part of the processing system. So as I discussed, the main brain of the entire computing system is actually the CPU. It's called the processor. And this takes all the decisions. Like, for example, if you write a program, this runs the program for you. And that too, it runs it very efficiently. So modern computers are very efficient, right? They're very fast. And all of this job, all of this work is done within the processor, which is pretty much the brain of the entire computer system. We will discuss the past, the present, and the future of computer architecture and why it's such an exciting field with a massive potential for jobs, innovations, as well as startups. So, let's go back. Let's go back 3000 years. So, ever since mathematics was discovered, man always wanted a little bit more of help, right? So ever since, why did we use maths in the first place? So we primarily used it for accounting, right? So early man, the moment that civilization came in, early man faced the need. Early man means our ancestors 3, 4, 5,000 years ago, they faced the need to have accountants and bookkeepers who could, for example, keep land records, keep records of payments, keep records of cattle, like I gave you 20 sheep, you give me back 30 sheep, right, with interest. Many of these things. So for that, what they did is they wrote simple programs, of course not in programming languages, but they wrote it in their mind to tally accounts. So I can maybe, hold on, just give me a second. So they use it to tally accounts. compute expenditures, and of course forecast future demands. So for example, it's possible that if the population of a village is increasing, so let's say this year they have 1000 people and 5 years later they forecast 2000 people, then they would see whether they would have enough water, enough grains, enough resources to sustain a population like this. So this is what our ancestors used to think of computing to be. Of course, they didn't use the word computing, but this was still in the back of their heads, and it did involve mathematical calculations, it did involve decision making, and that to us is computing. So let's take a look at ancient accountants. So this is a picture of an ancient accountant in Egypt. So you can see these hieroglyphic scrolls over here. You can see the hieroglyphic scrolls over here. So what he's actually doing is that he is maintaining the records, right? So I don't know hieroglyphics. I can't tell you what kind of records they are, but pretty much land records, salary records, payment records, say everything else that a rich man would like to keep. The moment you have a lot of money, you have a lot of resources, you would like to keep records, and that's where you need accountants, right? And accountants basically do computing in their heads. So this is the time that, let's say, we don't know exactly when, but many historians say 3000 years ago. That is when the first abacus came up in China, and so this was a very exciting computing device, because this, with a combination of beads, actually allows us to compute a lot of things, do a lot of mathematical operations, and that too very quickly. So it's a mechanical way of doing it, but very quickly we can do a lot of computation with an abacus, which otherwise was hard. So the abacus is still being used. Of course, it's not very popular, and a lot of kids do attend abacus classes, just to improve their IQ. But many old people in northern China, Russia, Mongolia, that area still use an abacus, particularly if they have been using it since childhood. So you do see a little bit of a calculator over here, but this gentleman finds using an abacus easier, probably because he can do it very quickly. And see, he is using an abacus, and that too very, very easily and quickly. And you can go to Wikipedia, so you will find more articles, and you will also see many more pictures. Unfortunately, they are under a license. I was not able to use them in this presentation. But you clearly can see that even when other electronic implements are available, this person is using an abacus. All right, so now let's move forward. Let's kind of fast forward by 2000 years, because other than the abacus, in terms of mechanical computing, which means dealing with numbers, nothing much happened until the advent of electronic current, right? So until electronic current and charge was discovered, nothing much happened. So once electronic current and charge was discovered, well, then you could make a very simple computing device to add. So let's say you want to add two numbers, well, you convert it into current, and you simply merge the currents, subject to losses and so on, but you simply just merge them. If you merge them, then the current, just by the Kirchhoff's laws, the current over here will be I1 plus I2. So we have a simple adder over here. We have a very, very simple adder. Similarly, because of Ohm's law, I can also implement a multiplier. See, if I have a control over the current, if I have a control over the resistance, right, with a rheostat, all I can do is I can multiply them. And this, in a sense, is like a proto multiplier. So I can sort of implement multiplication. I can, on the same lines, implement division. If, let's say, in current, I can control the voltage and the resistance, then I can implement division as well, and the final output will be the current. So this was kind of the main motivation behind developing an analog computer. An analog computer which was developed in the early part of the 20th century, and it was in use till roughly the 1940s, 50s, 60s. They did use simple currents and voltages to do their computation, which was again limited to simple add, subtract, multiply, divide. It did not have complex constructs that modern programming languages have, but it was still good enough for a lot of things. In fact, in 1969, it was analog computers that sent man to moon. They were not digital computers, right? So digital computers internally store data as zeros and ones. So there is a notion of what is called a state. What is a state? Well, a state represents a configuration of a system that does not change unless there is an external stimulus, which basically means that if I consider a transistor, its state remains as 0. Only when I do something to it, its state becomes 1. Then when I do something to it, its state becomes 0. So many of these early computers did not have the notion of state. They just given two numbers, they'll add it and they'll give it to you. But you can't say that add two numbers only if the previous addition was less than 15. Early computers were not smart enough to do that. Well, let's look at another kind of computer. So this is a mechanical computer, and if you look at it, this is made with a system of gears. So the system of gears is hardwired for solving a specific mathematical problem, in the sense that it is hardwired to compute ratios and products, right? So what we do is, if we turn one gear R1 times, the other gear, so one of the other gears that this is attached to will turn R2 times. So it is possible, but let's say by turning, this gear, another gear will turn, and by measuring how much the other gear is turning, that would give an answer to such kind of a mathematical problem. This, in a certain sense, has been used by Greeks way back in the 3rd or 4th century BC. And it has also been used by other people. But mechanical computers again had their heyday in the late part of the 19th century and again during the 20th century. But by that time, electronic computers had come in. So many of the early computing machines which people like Blaise Pascal and Charles Babbage used to make, which was again in the 17 and 1800s, it was to a large extent inspired by such mechanical computers. But again, the scope was limited primarily because there was a notion of the storage of state. And also, the other problem was that it still required mechanical effort as compared to electrical computers. These computers were large, bulky, and they were also slow because they were limited based on, mechanical speed used to limit them. So let us now talk of a different paradigm. So let us talk about water computers. So water computers utilize the flow of the fluid, water in this case, H2O, as opposed to a flow of electrons. So a water computer was developed sometime in the mid 50s, 60s, 70s. So this particular picture that you are seeing is a picture of the late 70s, early 80s in USSR. So many of you millennials who don't know what is USSR, well, it is the Union of Soviet Socialist Republics. It used to be 15 republics, Russia clearly being the biggest. Now they are separate countries, so they have become Russia, Ukraine, Latvia, Lithuania, Estonia, and so on. So now, the water computer's principle was simple, that you had a reservoir of water, there were pumps, inlets, outlets, valves, and finally the level of water in many of these small windows, that gave you the result of the computation. So the water computer that you're seeing over here was something that was on lines with the Soviet designs. I believe that this is a picture somewhere taken in a project in France, but of course I would ask you to go to Wikipedia and kindly check. So that is the source for this image. So, what do we learn from all of these things? What we learn from all of these different kinds of computing devices is that they were predominantly number processors, right? So, they used to take a set of numbers, perform a set of arithmetic operations on top of them. For example, they used to take two numbers, let's say A and B, compute B divided by A, put it in a variable called result. So this variable called result is the state element of the program because it used to maintain its value over a long duration of time. So that is the difference between logic and state. Logic is an operation and state is essentially a set of variables that maintain their value over a long period of time. The computer takes the program in as an input, which is the program that you write, and then what we get out of this is that it finally produces an output. The output that is produced, that output should be something meaningful, which is the output of the entire computation process. We can do the computation with either water, with either levers, with gears, with electrons as we do, or maybe we will start doing computations with many more kinds of fundamental particles in the future. So, quantum computers and so on. But the basic principle is this. So, what do they do? Well, they spend energy. When we move gears, we spend mechanical energy. When we move water, we spend mechanical energy. When we move electrons, we spend electrical energy, but we still get the result. What was known about computing till 1900 AD? That we have a task of things, a set of things that we want to do. The set of things that we wanted to do was called the program. In this case, this is the program. Furthermore, the notion of state and logic was well understood. That in this case, the variables represent the state A, B, and result. And the logic in this case are all the mathematical operations, addition, subtraction, multiplication, division, sine, cos, exponential, and so on. So that was the logic. All right. So this is the state and the logic. So this much was understood, but beyond this, nothing much was understood. Then came a gentleman called Alan Turing, roughly during the Second World War. So he was active in that period. 1930s, 40s. So he asked a very basic question. He said that if I want to implement a program, any program, what are the basic operations that need to be implemented? So let's say is add, subtract, multiply, divide enough? Or is it not? So will we have a program, a task in the future, which is impossible to complete if we just have add, subtract, multiply, and division? So how do we know that a computer has all the things, all the operations required to complete any task that man can think of, right? So it was a very, very important mathematical question that was very relevant for those days. And this is what the father of computer science, Alan Turing, started to work on. So if you think about it, the greatest computer architect of all time is actually Alan Turing, because he answered the most important question which led to the entire area called computer architecture. So an important discovery, I wouldn't say a discovery, well, it's a combination of a discovery and an invention, is the Church-Turing thesis. So two people, Alan Turing and Alonzo Church, they pretty much said the similar thing, albeit in very different ways. So Alonzo Church used a different paradigm to say the same thing, but ultimately it's the same, but Turing's version became much more famous. So what Turing said is that a function is computable by a human, right? A function is computable by a human being using an algorithm if and only if. So what's the algorithm? It's a sequence of steps. So if a human can do something, then the Turing machine, which Turing proposed, that also can do it. If and only if, right? So they're equivalent. So what he basically said that, look, anything that we can think of a Turing machine can do, and anything a Turing machine can do, we can think of. So this is a thesis. So a thesis by definition is not a theorem, so it cannot be proven. But it has been 80 years ever since, and we have not really found an exception. So he proposed a very, very simple mathematical machine known as the Turing machine, which he said is capable of solving all problems. So this was clearly a revolutionary idea. Even a revolutionary idea would be an understatement for those times, that such a simple machine was as complicated as the human brain, which people thought is extremely complicated, right? In fact, many ancient philosophers also believed that a lot of the computation we don't do in our brain, so they were not able to explain consciousness, right? They were not able to explain the basics or the basis of intelligence. And here came a man called Turing, who said, look, you take my machine, it's a simple machine, it's almost as powerful as a brain. So people were not able to relate that, but therein lies his genius. So what he said is that, look, let's take an infinite tape. So a tape is a mathematical device that he proposed, where essentially a tape consists of cells, where a cell can contain a value. So infinite means that the cells increase, sort of the tape extends infinitely in both directions. And you just have cells and you have a tape head that points to a given cell at a given point in time. Alright, you just have a tape and a tape head. That is all that you have. So along with that, we have a state table. So what he said is that the operation of the basic Turing machine is like this, that we read the symbol that is below the tape head. So as I said, it's a table. The tape has cells, and each cell stores a symbol. So we read the symbol. We access the state table. Based on this, based on what the state table tells us to do, we write a new symbol over here in the cell. So we can either keep the same symbol or we can change the symbol, right? So we write a new symbol. And then we move the tape head either one step to the left or one step to the right. That's all. So what do? We read the symbol, access the state table. Based on what the state table tells us, we either keep the same symbol in that cell or overwrite it with a new symbol. And then we move the tape head one step to the left or one step to the right. Well, this simple design did lead to the design of the modern computer. How? Well, you should take a course on theoretical computer science. You should take a course on complexity theory, you will get to know. But pretty much, three stalwarts, von Neumann, Eckert-Mauchly and others, they created a device from the Turing machine which had a CPU. So CPU, if you think about it, it is basically the engine that corresponds to reading the tape head and reading the symbol, accessing the state table, moving the tape head. All of that was encapsulated within the CPU. The tape itself was encapsulated in the memory. And of course, you need I/O devices to communicate with external agents, right? You need a monitor, a printer, and so on. So now we have the theoretical tools, right, which Turing gave us, Church and Turing gave us. So Church's work led to something called lambda calculus. So the lambda calculus is also a very important theoretical tool, but it's not used to the extent that Turing's work is used. So Turing's work, of course, gave us the Turing machine, which is now forms the bedrock of computer science. And then along with theory, you always need experimentalists. So that is when in 1947, the basic transistor was invented by Bardeen and Brattain. So it was a simple 3-pin device that acts like an electronically controlled switch. So these are examples of some of the early transistors, which you can see are simple 3-pin devices, which you plug into a breadboard. So these transistors were pretty much what were the key ingredient of early computers. But transistors initially were actually not used. They were used much later. Initially, people worked with vacuum tubes like triodes and diodes and so on. And that is similar to, same conceptually similar technology as a tube light, let's say. By the 50s and 60s, we had the theoretical achievements. We had the technological inputs that were needed. That began the era of computers. So where were we? So at in 1961, Gordon Moore, the co-founder of Intel, proposed the Moore's law. So here is what he said. What he said is that transistors will determine the evolution of computer technology, and furthermore, the number of transistors per chip will double roughly every year. That's what he said in 1960. For roughly 55 years, till around 2015, it held true that maybe if not every year, but 1 to 2 years, the number of transistors used to double, right? So it was like an exponential increase, and so even the 1 year increased to 2 years, but still it just kept on doubling. So that is how computers became that powerful, right? Because transistor sizes kept on decreasing. So what he defined was that we'll have a new generation where essentially the minimum, what is called the feature size, which is essentially the smallest dimension that we can fabricate reliably on silicon, right, which was used to build transistors. This decreased by a factor of square root of 2. So if both the length and the width decrease by a factor of square root of 2, the area decreases by half, and given that the area of the chip is the same, the number of transistors double. So a typical transistor is around 1 micron wide in 1980. It came down to 14 nanometers in 2016, and in 2020, which is now, we are at the 7 nanometer range, and the transistor technology will go down to 5 nanometers, but that's it. Because if you recall your high school physics, an atom is roughly It's roughly 1 angstrom, right? 0.1 nanometers. So 5 nanometers would be 50 atoms, and that is just about the limit at which we can fabricate these small transistors. They of course have high speed, they have low area, and they have low power, but this is quickly saturating. So computer architecture as of now is at a very exciting juncture where we have seen a lot of development over the last 50 to 60 years, and now we are going to enter into a new kind of era, which I will discuss. Okay, take the thumbs up from me. Let's go to slide 22. So this is again a plot on the log scale from 1970 to 2030. So we have not reached there, we're still at 2020. But the graph is still 2018. So it just shows you the evolution of Intel processors, Intel, AMD, Motorola actually. Over the years, the number of transistors they have been using. So you can see that they have been increasing in log scale. So these were the early Intel microprocessors. Then came the era of Intel desktops. Then these correspond to the mobile phones. And these of course correspond to the server processors that you use. And you also see AMD desktop and server processors over here. So regardless of what they are being used for, we see a steady increase in the log scale of the number of transistors per chip, and that gave us the additional power to play the expressive video games that we do now. It was all a direct consequence of the Moore's law. So where have we come to? We have come from 2000 to 2 billion transistors. In fact, many of the modern chips have much more. They have 10 to 15 billion transistors, and that's actually quite a bit, right? That's actually something substantial. So then we need to understand that how do we look at performance of these machines, right? So let's say if I were to ask you a question that, look, how fast is a mobile phone of today as compared to the supercomputer of, let's say, 1970? How would you answer this question? So the most important equation, something akin to the Newton's law of computer architecture, is known as the performance equation. The performance equation will help us answer this question, and that too very convincingly. So the first thing that performance equation tells you is that, look, there is nothing called the performance of a computer, it's the performance of a program, right? That's the first thing that you always say, that look, a given program, like let's say a chess program, runs 10 times faster on this machine. So how do I do that? Well, I run the same program on both the machines and I simply measure the wall clock time, which means I sit with a stopwatch and I measure it. So normally people say that one computer, if it has more frequency or more RAM, is better. None of that. Those answers are all wrong. You just run the same program on both places, measure the time, and that's it. See, if I were to break it, then I can of course break it into three components, very important components. Let me just erase the ink on this slide, otherwise you can't see. So the clock frequency. The clock frequency, for anybody who has taken an electronics course, they would realize that a clock is the most important element in a digital electronic system. So in digital electronics, a clock is pretty much like a periodic timer, which is needed for any digital circuit, such that it can finish its work in one clock cycle and write its answer somewhere in a state element, such that in the next clock cycle, another element can take the answer from that state element. So it's a way of enforcing timing. It's like a contract. So a clock in a digital system is more like, you can think of it like a contract, something like a school bell. So in high school, in middle school, primary school, when one period ends, we have a bell, right? Why is that? Such that people can go and attend the next class. So this periodic bell is like a clock in a digital circuit. So the clock frequency has increased from, kilohertz, I would say, right? 500 kilohertz in this case, to 3 gigahertz. Nowadays it's even more, it's around 4 gigahertz or so. And so the frequency is clearly a determinant of performance, where performance is pretty much defined as the ratio of execution times, right? Exec time ratio, time exec on processor 1 by time exec on processor 2. So that's how I would define relative performance, but absolute performance can be defined in this way. But I typically would compute a number like this. I might sometimes have a proportional sign over here and divide it by the performance of some known processor. Otherwise, I can also define it this way, right? A little bit of vagueness here, but doesn't matter. So as I said, the performance is proportional to frequency. It is proportional to the number of instructions in a program. So if we have a better compiler, like let's say GCC or the Intel compilers, what does the compiler do? It takes a program and produces machine code. Machine code is simply a sequence of zeros and ones that a computer can understand. So a better compiler technology has reduced by at least, reduced the number of instructions, reduce the number of instructions by at least 2 to 3 times. So as you can see, the performance is inversely proportional to the number of instructions. So fewer are the number of instructions, higher is the performance. So better compilers do produce more efficient machine code. Finally, another important thing is the number of instructions we can process per cycle, because a processor would typically take these machine instructions. What again is an instruction? So what we do is that we write a program in, let's say, C, C++, Java, doesn't matter. So then this high level program is too complicated for a computer to understand. So then what the compiler does is that it produces a sequence of machine instructions which are actually very simple. And it is like the state table of the Turing machine, which just has some very basic directives. So the dumb CPU can understand all of this, and it's just a sequence of zeros and ones. So it understands all of this, and then it executes. So a good computer can execute many instructions per cycle, many machine instructions per cycle. Hence, it increases performance proportionately. So what is the basis of modern computer architecture? That we have a program. The program is compiled, it is given to the processor, and in the processor that will execute, let's say in the steady state, n instructions per cycle. Then we say the IPC is equal to n, and we try to maximize this IPC as much as possible using architectural tricks. So these architectural tricks, which means whatever that goes on inside this black box, is basically computer architecture for all of us. What determines the IPC? Well, I will not talk much, because for beginners this can be too much. But what I can say is that inside the processor there is something called a pipeline. So the pipeline is where we break down the elements of the processor, we chain them one after the other. And of course, these can be very complex chainings, but the pipeline has a bearing on the IPC. We have a little bit of memory inside the CPU. We have a lot of memory outside the CPU. So many of you would have seen these motherboard cards where we insert memory. So of course, the memory size does help determine the IPC. So that is where the role of architecture comes in, which basically is in designing the memory system, which is how we store all our data, interact with variable, interact with state, and also with the design of this pipeline, which is the core of the instruction processing unit. Alright, so basically hundreds of techniques are there to make the pipeline more efficient. Hundreds of techniques are there to make the on-chip memory system more efficient, such that what can it do? Well, it can keep all the data that the pipeline needs close to it. So it should not be far away, like off chip it is very far and very slow. Whatever data it needs, it will just keep it close to it, such that all of this data can be accessed very quickly and the computation can proceed in a very, very fast and quick manner. Alright, and the off-chip memory also needs to be very efficient. The reason being that both from a power and performance perspective, it has an important bearing on the IPC. Alright, so what have we learnt? What we have learnt is that inside the processor there is something called a pipeline. The pipeline helps us process instructions, and in computer architecture we understand how this pipeline works. We can have simple pipelines where we just process instructions the way they appear in the program, or we can have complex pipelines where we do what is called out of order execution, which means we take these instructions, we mangle them, and we try to execute them in some other order such that we can execute as many instructions as possible. Right? So we have, let's say, instructions 1, 2, 3, 4. So we bring them into our processor and then we execute them in some order such that is the fastest possible way in which we can execute. And then when they come out of the processor, they come out in the same order in which they came in. So such notions of out of order execution are very important. Many times what we do to improve the performance of a processing system, we predict values. So why do we do that? Well, sometimes it takes a lot of time to, let's say, get the value of a variable from memory. Then the question is, should we wait? Probably not. So let's first consider this. So let's say that I have some variable. The variable is physically there in off-chip memory. It will take me long time, which means hundreds of cycles to get it. Let me try to make a guess. Let's say that historically its value has been 5. So let me try to make a guess and let me try to guess that its value has been 5. And let me proceed with this. Alright. If I proceed with this, then what will happen is that I might be correct. If I am correct, I'll gain performance. If I am not, I'll have to redo most of the work. So this is known as speculation. I can speculate on this. Let's say there is an if statement. I can speculate on the direction of the if statement, whether it will be an if or an else. I can speculate between dependencies between instructions. So I can say that, look, it's possible that one instruction does not produce something that another instruction will consume. I can also take the time speculate on whether I will get a value of a variable in on-chip memory or off-chip memory. So essentially what I do, the crux of all of this is in a modern computer architecture, I make there's a lot of guesswork, right? For the sake of improving performance, particularly the IPC, there's a huge amount of guesswork. So this guesswork, what we call in computer architecture semantics, is known as speculation. So then what happens is that because I have so much of speculation, it is possible that most of the time I'll be correct. But occasionally if I am wrong, I need to fix whatever mistakes I would have done. So this is the thing, I need to what I call roll back and recover, which means fix mistakes. So modern computer architecture in that sense is very interesting because architecture has been doing learning way before machine learning used to do. In the sense in architecture, we actually do a lot of prediction, a lot of learning Prediction based on learning. And we try to predict the values of variables, we try to predict the values of branches, we try to predict a host of things. And then, of course, if they are wrong, we need to find ways to ensure that our program's execution is correct. Where did we reach with all of these tricks, right? The last 3 slides were heavy, but that was just to give you some idea of the depth of computer architecture. So with all of these tricks, where did we actually reach? So if you see this huge cabinet sized machine, right, which is a part which looks more like a library and less like a machine, it looks like a kitchen actually, right? It's so big. But this, believe it or not, was the revolutionary, legendary IBM 360 computer in the early 60s. This is a modern cell phone. How fast is a modern cell phone as compared to IBM 360? Well. So IBM 360 falls down flat and Samsung S5 stands tall. The reason is that it is roughly 10,000 times faster. So believe it or not, this small cell phone, as opposed to this massive computer, this is 10,000 times faster, only because of advances in transistor technology and computer architecture technology. So we discussed the past. Now let us discuss the present briefly and the future even more briefly. So in the present, what has happened is that if I look at these dates from 1999 to 2012, and the y-axis here is a clock frequency, we see that it has remained, we see that it has remained roughly constant for the last 13 years, and of course now it is 2020, so it has still remained constant. So the clock frequency is not increasing. Why is it not increasing? That is mainly because of power and temperature issues. Because of power and temperature related problems, the clock frequency of a processor is not increasing. So we are not able to increase performance via that route. Similarly, the performance of a single core, what is a core? It's just one processor. So even in a mobile, we have 8 cores, which means you have 8 processing units. You can run 8 programs in parallel. So one core can only run one program at a time. So even if we see what is called the spec score, which is essentially a relative performance, this has started to saturate after 2008 or so. So it has not really increased. So this is a small image that I was able to download freeware, and what this says is that look, modern processors produce so much of heat that it is actually possible to fry an egg, right? You can see a nice double poach egg over here just with the heat that a processor generates. That is because power is proportional to frequency cube. So if we double the frequency, we would actually increase the power by a factor of 8. So modern processing multi-core processors, right, with multiple cores, that would easily generate 150 watts of heat. And if I would consider memory and the hard disk and so on, we might be talking about something in the range of 200 to 300 watts. And if we have a graphics processor unit, that might be an additional 200 watts. And if you think about it, a half kilowatt, a small device that generates half a kilowatt, it's like a heater, right? So you can easily fry an egg. And that's exactly what you get to see over here. Hence, we cannot increase the frequency anymore. What's next? Well, even in terms of compilers, we are seeing diminishing returns. Even in terms of IPC also, we have exhausted a lot of tricks. Does it mean that computer architecture is dead? Well, the answer is no. We will see why. Single core computer architecture is mostly dead in the sense that having a single pipeline is dead. But a modern architecture, we have a think parallel mantra, where instead of having a single pipeline which can run one program at a time, we actually have a multi-core architecture. Multi-core means if these were the cores, we have a lot of cores and we can actually run separate programs on these cores. And we can also take a same program and split it into many sub-programs and run it on these cores. So pretty much parallel is the future. All right. So parallel computer architecture, which has been around since 2010, that is pretty much the future, right? So that is where most of the innovation has happened in the last 10 years, and it will also continue to happen. So we'll have cores, cache banks, memory controllers, other circuitry. And but the crux is that we will have a lot of cores. For each core is one processing element, where we'll run multiple programs at the same time, or take the same program and split it into many sub-programs. For example, I am using a video editor to produce this video. So when I would finally what is called render the video, which basically means take the raw video and produce the video that is going to be uploaded on YouTube, it will actually divide the work into several sub-programs, give some of these to the different cores that I have on my laptop. My laptop also has a GPU, a graphics processor unit. So some work will also be given to the GPU. And after that, the final video will be created. What are some of the new problems to be solved? Well, since we are thinking of parallel architecture, writing parallel programs, efficient parallel programs, converting existing sequential programs to parallel programs, the design of parallel architectures, which are easy to program, and of course designing efficient memory systems for parallel architectures. All of them fall within the ambit of parallel programming. Trade-off, well, how many cores should we have? What should be the performance per core? The frequency of each core? Should we have all the cores, should they be at the same type? Probably not. So many of your ARM cell phones have several small cores. They have several large cores. What should be the mix of small and large? So there are many important research questions that need to be answered over here, and that would determine the performance of the final system. What about cooling? A lot of innovation is happening over here. So previously you would have seen a small fan on top of the processor. What that small fan used to do is that used to do forced air cooling, right? What is called convective cooling. But nowadays what is kind of in fashion is this water-based cooling. So what we actually do is that we have these water pipes, which you can see over here, nice colored water pipes. What these pipes are doing is they're moving these coolant fluids throughout the desktop over here, right? It's more like a server processor throughout the machine over here, and pretty much everything is being cooled very nicely. So this is an example of a futuristic cooling system which has come out a few years ago. It's still not commonplace. A lot of this research will happen in the coming decade, which is this decade, 2020 to 2030. What else? So we can have something called process variation. So what are we trying to do? Can you do fine-grained calligraphy with a blunt knife? Well, the answer is no. Then how can you design 14 nanometer transistors with 193 nanometer light? What you will end up doing, you want to draw a structure like this on silicon. The structure is essentially going to come more like a bone, like this on silicon. So what should you do? Well, so what you should do is first is realize the gravity of the problem. So the gravity of the problem that I had, something that we teach in class all the time, is that let us have this image over here. If let's say this is what we want to print on silicon, this is basically 4 transistors. This is how 4 transistors would look on silicon. What you will actually get is this. So note the rounded corners, right? You can see all the rounded corners over here, and this is clearly not what we want. But why is this happening? Well, this is happening because the size of the transistor is less than the wavelength of light. So because of diffraction effects, diffraction related effects, we are seeing this problem. What do we do with this? Well, since we cannot accurately fabricate transistors, their performance will vary from specifications. We need to have error tolerance, timing margins, right? So we have to design an architecture that will take care of these things. So we need to create what are called process variation tolerant architectures. What about reliability? So once one of my students asked me that if cooling is such a big problem, then let us take our computers, these large computers that we have, on top of the Himalayas. Let us take them to Tibet and let's just have them over there. Let's take them to Kashmir, right? So there no cooling is required. All the cooling that we require there is we just open the windows. Well, that's not possible. There is a problem. So what I am doing here is I unfortunately cannot run a processor for 10 years, or if I have 1000 processors, I cannot run them continuously for 10 by 1000 years, which is 1 by 100 years, which is 3.6 days. The reason is that there will be a problem. Most processing units are bombed by different cosmic particles. So we of course don't get to see them, but they do affect our processors and our transistors quite a bit. What are the major offenders? The major offenders, well, I shouldn't say beta particles, there are alpha particles and neutrons, right? So all of you would be familiar with alpha particles and neutrons. So they keep on bombarding the processors, they keep on bombarding the transistors. Whenever they bombard the transistors, it leads to a displacement of charge. Whenever there is a displacement of charge, there is a current pulse, and the current pulse can go and it can flip the value of a bit. So imagine you have a bank account and a bit gets flipped. Suddenly you either become a millionaire, or from a millionaire you come down to somebody who owns just thousands of rupees, right? That would be a problem. So because of that, architectures have to be tolerant to such particle bombardments, which are called soft errors. And this is a major concern in the design of architectures. And this is why there is a need to work on them and do a lot of things to ensure that even if soft errors do happen, they don't lead to failures. So most modern memories are soft error tolerant to a very large extent. So they have something called error correcting codes to detect and correct from soft errors. But memories are protected. The processor itself is not protected. Alright. If I run a processor again for 10 years, what else can happen? Just look at this little wire over here. What you can see is that this wire, which used to be one uniform strand of copper, it is not a uniform strand of copper anymore. You can see a lot of breaks, right? You can see breaks over here, you can see breaks over here. So it is like a breaky wire, and this part of the wire has become very thin. And so the resistance here will be very high. The localized temperature here will increase. And this will lead to a further thinning of the wire. This is known as electromigration, where what happens is that along with the current, there is a slight movement of mass. So if let's say current is moving in this direction, so in this case, what you get to see is that one side of the wire is kind of thin and rugged, but the other side is strong. So what happens is that when electrons move in one direction, they pretty much also take away some protons and neutrons along with them. So pretty much mass moves. So in this case, if the electrons are moving in this direction, what they are doing is that they are moving some of the mass of the wire, which is the copper, along with them. And this is leading to thinning. Wherever there is thinning, there can be breakage. And once a wire snaps, the entire processor is gone. So this also limits the reliability of the processor to a large extent. Now what about security? So let me now say something which I have read in numerous spy novels and in the newspaper. My apologies if this is not accurate, but I'm just going by what has been published in the popular press. So in September 2007, Israeli jets bombed a Syrian nuclear facility. The Syrian radar had mysteriously stopped. So here is what I get to read from spy novels, which claim to be authentic, but they claim I don't. The scoop is that Israelis sent a wireless message to the processor in the radar, Then the message was able to hack the processor in the radar and it shut itself off. All right. How do you make, so this is known, so this by the way is known as a kill switch. It's known as a hardware Trojan. And the research problem is that how do you make a design tolerant to such hardware Trojans? Because otherwise what will happen is that, let's say somebody fires a missile at you, you hack into the software of the missile and you make it turn back and then it hits the place from where it was launched. This story, which again I don't vouch for authenticity, it is something that I have picked up from the popular press, but assuming even a part of it is correct or it is inspired by some other story which is true, it does tell you about the potential of hardware and software hacking that would primarily concern nuclear and military installations. So there are also similar stories of what happened in the nuclear reactors of Iran, for example, where a bug, a worm, which is like a virus called Stuxnet, so that created a lot of havoc. So pretty much for us nowadays, with the proliferation of mobile phones and Internet of Things devices, security is becoming a very, very important concern, and this is something that should be addressed. Alright, so we have discussed the present. What was the key takeaway from the present? The key takeaway was that a large part of conventional computer architecture, which was essentially making a single core faster, that part is dead because of power and temperature issues. But many modern aspects such as parallel computing, parallel processing, reliability, security, power efficient design, these have all been hot topics of the last decade and still continue to be. What about the future? Well, future is hard to predict. It's a mystery. As they say, the past is history, the future is mystery. Well, let's try to project. So currently we are at 7 nanometers. 2022, we don't know. We might be at 5 nanometers. As I said, that's only 30, 40, 50 atoms wide. So we place a few atoms go here and there. The specifications of the transistor will deviate substantially. So we clearly cannot scale silicon beyond this. So silicon is kind of reaching the end of its life. Well, if silicon is reaching the end of its life, are we at a dead end? No. So there are many, many more devices that are coming up which will take the place of silicon. Well, what will, I cannot say right now, because all of these devices are pretty much in the contention for replacement of silicon, but they still are in various stages of development. So one of the most promising is graphene. So graphene is not graphite, even though it is something similar. So it is one 2D sheet of carbon. So it is two-dimensional, one atom wide. And it has some fantastic properties, particularly in terms of power efficiency and frequency. So graphene can clearly be a replacement for silicon if we can mass manufacture. Next comes spintronics. So in spintronics, we rely on the spin of the electron. Alright. So what we do is that the spin of the electron is what we rely on. That's what stores the state. And that is what we use for computing. Quantum computing, you would have heard a lot about it, particularly with the recent announcements of IBM, Intel and Google. So in this case, what we do is we store information in the quantum state and we define something called a qubit, which pretty much, if I were to explain in half a sentence, it is like storing multiple bits at once. It's not really that, but that's as far as I can go at the moment. So quantum computing will clearly not replace traditional computing because there are a large number of traditional algorithms which are very, very inefficient quantum implementations. So there are a very small class of algorithms that are quantum efficient. So those will run on quantum computing, but quantum computing is at best something that is supplementary. It will clearly not replace. A very, very promising candidate is using photons. So photons and electrons are essentially different kinds of fundamental particles. One is a boson, the other is a fermion. One advantage of photons is that they are not associated with mass. So they do not have many of the good properties that electrons have, in the sense we cannot store photons, we can't create a capacitor. But on the other hand, photons are not associated with an I square R loss. So that's the reason they have fantastic power efficiency properties. But we still are yet to build and demonstrate a clear photonic transistor. So that has not been built, even though a lot of research is going on. Now let's come to the teaching aspect, right? So I did promise you a very brief future, which hopefully I was able to explain some part of it. Now coming to teaching, say any first year student in engineering in the computer science or electronics fields is expected to do a few courses in computer architecture. Most are mandatory. So what do you do? Well, you start with Boolean algebra, which is algebra that uses bits instead of other things that you're used to. And it's essentially algebra of Boolean bits. We talk about how numbers, strings, etc. are all represented using bits. Then something called assembly languages are taught, which are essentially machine. They are not as low level as machine code, but pretty much one line of assembly corresponds to one line of machine code. So typically the ARM and x86 assembly languages are taught. Digital logic, so how do we build digital circuits? And then of course computer arithmetic, how do we add, subtract, multiply, divide in computers. After the basic course, then of course processor design is taught, how do we make a single core, and then the more efficient version of processor designing called pipelining, which I have discussed. After that, an important component is memory systems. So in memory systems, on-chip memories are taught, which are called caches, which means the memory that is there inside the processor. And then off-chip memories are taught, called main memory, which is there on the motherboard. Then we come to multiprocessors, which is the second half that I talked about, multiple cores. And finally IO systems, because no computer is complete without IO systems. So that would include monitors, printers, network, hard disk, all of these things. That's the second part of the basic course. Then if you come to advanced topics, so advanced topics, so that is where I would like to do a little bit of publicity of my upcoming book that is coming out in 2021. So actually the basic course is also part of my earlier undergraduate book published by McGraw-Hill in 2015. And the advanced topics is my second book that's going to be published in 2021. So there, of course, modern out-of-order pipelines are discussed. GPUs, graphics processor units, which are specialized processing systems for graphics, games, videos. Then theory of memory models, which talks about multiprocessing, security, of course, low power. And a very exciting area, other than, of course, caches, main memory, is processors for machine learning. So this area has really come up in the last 2 or 3 years, particularly with the advent of more machine learning applications. Nowadays, even if you buy a smart TV, you don't have to change the channel. You just tell the TV, go to channel 350, it goes there, right? So it has a very fast module to recognize voice, convert that into text, and do whatever is being said. So processors for machine learning does feature in a course on advanced computer architecture. If you will also find it in my book. Thank you very much. I hope that I was able to introduce the area of computer architecture from 2000 BC till 2000 AD to some extent. This is my email address. Please mail me if you have any queries, and kindly subscribe to this channel. I'll keep on adding computer architecture videos on this channel.